Hi everyone, this is the gas walkthrough for June 4th. I'm Philip Newman. I have graduated to a removable brace, and I'm not going to require surgery or anything, just need to keep my hand still, or at least a couple of fingers on my hand. But today I'm solving Always Alright by Bill Murphy. This is a quadruple Sudoku. So we have normal Sudoku rules, 1 to 9 each row, column, and 3x3 box. Having to do this very carefully left-handed. And we have some white circles, and the digits in those white circles must appear in the surrounding 4 cells. So somewhere in these 4 cells is a 4 and a 6. When we have duplicates, those digits must appear twice in the surrounding 4 cells. And that's very important in this puzzle. Obviously, we have lots of duplicated digits in our quads in rows 3 and 4 and in rows 6 and 7. So let's talk about what we can do with those. And we're going to start at the top because the breaking at the top is a little bit easier. We know 4 and 6 are in these cells somewhere. So we know this is not 6. So how do we fit 2 6s around the circle? Well, the only way we can do that is with 6s like this. And as soon as we have a 6 in this cell, we know it's not a 7. So where do 7s go? They go in these cells, 8s in these cells. And then back this way, 5s, 4s, 3s, 2s, and 1s. And that leaves 9 on each end. And we can see here we need 5 and 6 in these cells. We can actually resolve that. We'll come back to that. We need 2 and 3 in these cells, and we need 4 and 6 at the top, and that's resolved because of this 6. So this is our 4. Now, we can resolve both of these pairs by looking down here. We know there are 2 5s in these 4 cells, so that means one of the 5s has to go in this column, so there's no 5 here. So 6, 5. You can do the same here with 2s. 2 is in one of these cells, so that's 3, 2, like that. So that's a good start at the top. We can actually place 5 and 1 in this box. We can place 4 in this box because of this 4. These are 7, 8, 9. These are 1, 2, 3, and these are also 7, 8, 9. Okay, down here, a little bit trickier, but we're going to reference what we did up here. Here we had 1s and 2s and 3s all going in the same diagonal direction. And what we were left with was 9s at each end. So we're going to have the same sort of thing here. We could have 4s like this. Could have this. And that's going to leave 3 in this cell and 3 in this cell. So that's one possibility. The other possibility is we have 4s like this, and so on. And that's going to leave 3 in these cells. One of those is impossible, though, because we have a 3, 7 quad down here. So we know 3 is on one of these 4 cells. It's not here. So where does 3 go in these 2 cells? It has to go here. And it has to go here. There might be a clearer way to look at that. I'm not entirely sure how else to explain it. I guess we could think about where does 3 go in this row. If 3 went in any of these middle cells, we would have a problem. Because, for example, if we put a 3 here, where do 7s go? And where do 6s go? Well, they need to go there too. So that doesn't work. And it can't go here because of the 3, 7. So however you want to look at that, that's a little tricky to find if you're not familiar with these sort of patterns. But that's what I'm going to use. And it's entirely possible there's another way to break into this puzzle. That would not surprise me. These are 3, 4, and 5, and they are resolved by the digits in the columns. We need a 4, 5 on this quad. and they go in that order. Here we have 8 and 9, and these are going to be 6 and 7 in some order. Here we need 1 and 9, so this is our 9, 1, and here we need 3 and 7, that's also resolved. It's going to resolve 6 and 7 here. We need an 8 and a 2, resolved by this 8. In this row we need 1, 4, and 5. 4 and 5 are resolved, so that leaves that spot for 1. These are 2, 3, and 6. The 6 goes here, and then 2 and 3. It's going to place 1, 3, 2. We have 2 7s looking up, 2 8s looking up, and then 9 goes there. And then we have that's 6, that's a 9, 2, and a 1. And then these are 6, 7, and 8. You can see a 6 and 7 in the column. And then finally 7, 8, 9 to finish it off. And that is how you solve Always Alright by Bill. This is a neat pattern. I always enjoy things like this, but it can be tricky to break into if you're not familiar with it. So let us know how you found that in the comments. I would be interested if anybody broke into this some other way. And I will see you next time.